everyone. So this video is for the 7.8 worksheet. So the very first page of this worksheet, we're actually going to revisit some of the ideas that we've seen before and then build on those ideas. Okay, so what I want you to do is draw just a quick rough sketch of the sine function and the cosine function. So go ahead and pause the video while you do that. And then this is what you should have for your two graphs. Okay, so number 2, what is the input quantity for both the sine and the cosine function? So with both of these, the input is going to be our theta, which is going to be our angle measure. Okay, and then number 3, what is the output value for the sine function? So remember, the sine function looks at the vertical distance. And then part 4 is looking at the output for the cosine, and the cosine always measures the horizontal distance. Okay, and then next we want to know what is the domain and the range for each of those functions. So the domain for the sine function is going to be negative infinity to positive infinity, because we can take our circle and just go around and around and around, and so we can keep adding degrees or radians to our circle. And then the range on a typical unit circle oscillates between -1 and +1, right? So the lowest that our function is going to be on both of those is -1, and then the highest peak is going to be +1 on just our standard sine and cosine functions. And then the domain and range for the cosine function is going to be the same thing. So even though we're looking at the horizontal distance, our angle measure can keep going. We can keep rotating that wheel, and then the range is -1 to +1. All right, so number 7, we're now going to start thinking about the inverse functions, which you should have seen in previous math courses. So the inverse, the big idea with inverses is that the inputs and outputs are going to switch. So when we say what is the input quantity for the inverse of the sine function, right, that means that it's the old output. Okay, so let's go up to our graph. So the input on the original function was theta, the output was vertical distance. And so when we think about the inverse, the inputs and the outputs switch. So the vertical distance is now going to be the input, theta is going to be the output. Answer is part 8. So the output is going to be our sine. So inputs and outputs switch on inverse functions. Okay, number 9, is the sine function invertible? How do you know? So when we look at our sine function, the way to know if something is invertible is, does it pass the horizontal line test? So if we think about drawing a horizontal line, we know that that output is going to exist in at least 2 different inputs. And so because the output maps to more than one input, it is not invertible. So it's not invertible, does not pass the horizontal line test. Okay, but then the bigger question is it possible to make the function that is not invertible, invertible? And if so, how do we do that? And so in college algebra, hopefully you've talked about that. In order to make it invertible, we restrict the domain. Okay, so what I want to do is look at our sine function. Okay, so when we look at our sine function, what we want to do is be able to restrict this domain so that it does pass the horizontal line test. And so if you look at our graph, if we block it off and just like think about covering up this section of the graph and then this section of the graph, it does not pass the horizontal line test, right? So if we draw that horizontal line, it's still touching in two different spots. So if we think about restricting it in another spot, okay, so if we think about restricting it from here to here, that does create a function that passes the horizontal line test. So if I draw a horizontal line, it only touches the graph once. So no matter where I draw that horizontal line, it's only hitting that graph once. Okay, so it looks like on this particular graph, if we restrict the domain from pi over 2 to 3 pi over 2, that would allow us to have a graph that is invertible. Okay, one of the things that mathematicians decided a long time ago, and you'll see why in just a couple minutes, they decided to restrict the graph from negative pi over 2 to pi over 2. So if we extend this graph in the other direction, so there's negative pi over 2, if we restrict our graph here from negative pi over 2 to pi over 2, that still passes that horizontal line test. Okay, so we're going to restrict the domain from negative pi over 2 to pi over 2. And that allows us to have a sine function that is invertible. Okay, let's go ahead and go to the next one. So we're going to think about our sine function and where we're restricting it. So I'm going to go ahead and draw that negative pi over 2 to pi over 2 for our sine function. And then the reason why we restricted it here is because the negative pi over 2 to 0 degrees, that represents quadrant 4. So the negative pi over 2 is that 6 o'clock position. There's the 0. And then from 0 to pi over 2, that represents the first quadrant. So this is quadrant 1. This is quadrant 4. Okay, and then when we think about our cosine function, we want to think about where we want to restrict that function. So if we take our original cosine function, so in order to make the cosine invertible, mathematicians have restricted this function between 0 and pi over 2. So if we restrict the graph here, notice that this does pass the horizontal line test, which means that it is going to be invertible. So from 0 to pi, we have our cosine function. And when we think about our circle, the pi over 2 is our 12 o'clock position. Pi is our 9 o'clock position. And so that angle measure is going to represent quadrants 1 and 2. So when we restrict our sine function between negative pi over 2 and pi over 2, that relates to quadrants 1 and 4 on our circle. And then if we restrict our cosine function between 0 and pi, that gives us quadrants 1 and 2. Okay, so now let's take a look at an application problem so you can see why we are looking at functions being invertible. Okay, so we've got Savannah is sitting in a bucket of a Ferris wheel at the 3 o'clock position. The Ferris wheel has a radius of 62 feet, so let's make a note of that. Radius equals 62. The Ferris wheel is going to be moving in that counterclockwise direction. And we want to know what angle or angles has Savannah rotated from our 3 o'clock position when she is 42 feet above the horizontal diameter of the Ferris wheel. Okay, so because our radius is 62, we know that this spot right here is going to be 62. We know that the 12 o'clock position is going to be 62 as well, because that's our radius. When we go to our 9 o'clock position, that is showing negative 62, which means we are 62 units to the left. And then here, This is a negative 62, which means we are 62 units below. So we get those values from our radius. What we want to know is when Savannah is 42 feet above the horizontal diameter. So 42 is about right here. It's about 2/3 of the way up. Notice that if we're thinking about this Ferris wheel, so there are two separate times when Savannah is 42 feet above the horizontal diameter. Okay, so we want to find both of the angles to each of those points. So on this first circle, I'm going to go ahead and find this angle right here. So this is our theta. Okay, so we know from previous worksheets that our sine function measures the vertical distance. So vertical distance is our y value equals r sine of theta. And so what we want to do is plug in the values that we know. Our y value, we know that our vertical distance is 42. That's the y value we're looking for. We know that our radius is 62. And then we have sine of theta. Remember, theta is what we're looking for. We're looking for what angle has Savannah rotated. So this is the first time that we are solving for the input on our trig functions. So what we want to do is isolate our theta. To do that, we're first going to divide both sides by 62. So we get 42 over 62 is equal to sine of theta. And then we want to take the inverse of this sine. So remember earlier I mentioned that inverse functions, we switch the inputs and the outputs. So we're going to do the same thing here. So the input and outputs are going to switch. Let me show that in color. So inputs and outputs are going to switch. So this becomes sine inverse. Remember our notation for inverse is, it kind of looks like a -1, but it's not that value, it just looks like it. But that's our notation for an inverse of sine. The input is now 42 over 62 equal to theta. So this allows us to isolate our theta. It gets theta all by itself. Okay, so you will see on your calculator that you have inverse functions already pre-programmed. So on your calculator, you're going to hit sine inverse, and then a parenthesis should show up, and then you're going to do 42 divided by 62, close off that parenthesis. Okay, and then depending on which mode your calculator is in, you might get 0.74, which means that your calculator is in radians. If you ended up with 42 as your answer, that is because you are in degrees. And so in this particular question, it didn't specify, do we want it in radians or degrees? So both of those answers are acceptable. Okay, so you do want to be careful. We are looking for all possible angles that would be 42 feet above the horizontal diameter. So this solution just gives us one of the angles. So if you're in radians, it's 0.74. If you're in degrees, it's 42 degrees. But remember, we have this second blue dot, so we need to find that angle as well. Okay, I'm going to go ahead and draw that second dot on this new circle. And that means we're now looking for this angle. We again always want to start from our 3 o'clock position. Okay, so the reason why that domain question earlier was so important is because notice that this dot is in quadrant 2. On the previous problem, our dot was in quadrant 1. And so when we plugged it into our calculator, the calculator was able to give us an answer when we were in quadrant 1. But if we look at this visual, our sine function, we restricted the domain between -π/2 and π/2, which means that any point in quadrant 1 or 4 is the value our calculator will give us. But since our new point is in quadrant 2, our calculator will not be able to give us the solution. So we have to use our reference angles. And we talked about reference angles in a previous worksheet. Okay, so what I'm going to do is draw the previous angle that we were given right here. And we know, I'm going to go ahead and use degrees when I explain this because degrees are more familiar to students. So we know this was 42 degrees right here. Well, by symmetry, that means that this angle right here must also be 42 degrees. Okay, and so remember, we want this blue angle that is showing up right here, so from our 3 o'clock position all the way to this blue line. Well, if we go halfway around the circle, that's 180 degrees. And we want to take away the 42 degrees. We're going to take away this part of the angle because we don't want that part of the angle. So 180 minus 42 degrees gives us 138 degrees. Okay, so that means that from the 3 o'clock position to this line, that gives us 138 degrees. If you wanted to think about it in terms of radians, we could do that as well. Okay, so in radians, we would have 3.14, so that's halfway around the circle, minus the 0.74 that we found from the first point, equals 2.4 radians. Okay, so when Savannah is 42 feet above the horizontal diameter in quadrant 2, that angle is going to be 138 degrees or 2.4 radians. Okay, let's go ahead and take a look at another problem. So what angles has Savannah rotated when she is negative 20 feet to the right of the vertical diameter? Okay, so I know that language is a little funky, but the big idea is we needed to have that negative written in there so that way we include the negative in our equation. Okay, so negative 20 feet to the right means that technically we're just 20 feet to the left. And it's just a continuation of the previous problem, so that means that our radius is still going to be 62 all the way around. Okay, so 20 feet is going to be about a third of that distance. And so we want to think about all the points that exist when Savannah is 20 feet to the left. So there are 2 points. The first one is going to be in quadrant 2, and then the second one is going to be in quadrant 3. So that means, again, we're going to be looking at 2 different angles for our solution. So I'm going to draw a line from the dot to the origin, and then we're looking at the angle from our 3 o'clock position. Okay, one of the things that I want to highlight here is that now we are measuring horizontal distance, right? We're thinking about 20 units to the left. So horizontal distance, let's make a note of that. Which means we are now going to be using the cosine function because the cosine function measures horizontal distance. Okay, so that means that we're going to use the equation x for horizontal distance, r cosine theta. So our x value is going to be negative 20 equals, our radius was 62, cosine theta. And then just like before, we want to solve for that angle. So that means we want to isolate that angle. We first are going to divide by 62. So we are left with negative 20 over 62 equals cosine theta. And then in order to isolate that input, in order to isolate our theta, we are now going to take the inverse, which means that we switch our inputs and outputs. So that gives us cosine inverse of negative 20 over 62 equals theta. Okay, again, the entire point of finding the inverse is so we can isolate that input. Okay, and then go ahead and plug this into your calculators, and we can get one of 2 answers. So it's either 1.9 radians or you might get 108.92 degrees. So both of those measure this angle, getting us to the point that is 20 units to the left. Okay, and then because we can also potentially have that same distance to the left in quadrant 3, let's look at this new circle. Okay, let's go ahead and put the dot in there to represent that we are 20 units to the left. Okay, and now we're looking at the angle still from our 3 o'clock position all the way to that line. We call that the terminal side. Okay, so if we go back to when we referred to domains, we said that our cosine function, we're going to restrict between 0 and pi, which means that the calculator is going to be giving us angles that exist in quadrants 1 or in quadrant 2. But this point right now is going to be in quadrant 3. So because that is not part of our domain, we will have to use reference angles to find this solution. Okay, our calculator did give us the angle from quadrant 2. So we know that this is 108.92 degrees. And there's a couple ways to reason through this. So by symmetry, if this is 108, that means that this angle right here is also going to be 108 degrees. And so if we think about the orange angle that I've shown here, that would give us, if we take that orange plus the purple, that gives us a total of 360 degrees, but we don't want this 108 degrees right here. So we could take 360 minus the 108.82, which gives us 251.18 degrees. If we thought about it in terms of radians, we could take 6.28, which is the full circle, minus the 1.9 that we don't want, and that would give us 4.38 radians. And so these two solutions give us the second angle when Savannah is 20 feet to the left of the vertical diameter. All right, that is it for this video. We will do a few more examples in the next video.